right, let's get started. So, as I told you from yesterday, that the midterm to be decided either to be on Wednesday or a Monday. So the midterm will be, it's already decided, and it will be on Monday, July 12th, and it's in the lecture time starting from 9:45 a.m. And actually, this was sent in an announcement here. So yeah, just like make sure that you are reading, you guys are reading the announcement. So the midterm exam will be on Monday, and here's more details and the coverage of the exam and how you prepare. And I will keep sending some emails to how to prepare for the exam. And actually, we will have a review lecture before the exam. So just like to prepare yourself, how to study and how to tackle problems and how to identify how to tackle problems. So we will be having a revision before the exam. So do you have any question, David, before I start? All right, so let's get started here. So today we will be talking about two topics. The first topic is chapter 14.4, which is the power and efficiency. And it's something like depends on the concept of work that we have been dealing with over the last couple lectures. So power is defined as the time rate of change.
Professor, I'm not sure if you're speaking because I can't hear any audio on the Zoom call.
Oh, you cannot hear me? Oh. So how about now?
Yes, there we are. That's much better.
Okay. So let me do just like a quick test here, just to make sure that the audio settings. So yeah, same as the system, it should be good now. So you hear just like final confirmation, you hear me
Yes.
very well?
Yep. I can hear you speaking. Yeah.
Okay, sounds good. So the power is the time rate of a change of work, and we know from the last couple lectures that that du is equal to the force dot product by dr, and from this we were able to integrate and get the work from point 1 to point 2 and get in here from R1 to R2, and this is equivalent to from S1 to S2 after divide this dot product, and it will be F cosine theta ds. So this is how we get the work. So for the power is equal to the time rate of a change of the work du by dt. And if we put this in the dot product form, so this will be f dr, just like putting this here, and we have dt down there. So this will be the force multiplied by dr dt. And as we know, this is the time rate of a change of the position, which is the velocity vector. So it will be the force vector dot product by the velocity vector. And the units of the power, as we know, but let's just like start from work. We know that the work is force multiplied by distance, so it's in Newton meter or joule. And we know that the power right now is a work divided by time, so it will be Newton meter over second, or which is equal to joule over second. This is in the international system unit, SI system. In the US unit, it will be pound foot over second, and this is the US system. And from here, we need to define two important things about the power. So we know that the power is usually measured by watt, and this watt is equivalent to the SI unit. So this is equal to watt. And we also know that there is another unit for the power. It's called horsepower. And let's put this note here. 1 horsepower. Sometimes you will be given in the problem that the power in this problem is like 5 horsepower or 20 horsepower. So 1 horsepower is equivalent to 550 pound-foot per second, and it's equivalent. This is in the US units, and it's equivalent to 745.7 Newton meter over second. So you should know these. I think it's in the dynamic sheet, just like double check. Because whenever you are given in the problem, the power of this motor is 5 horsepower, so you will need to transform it either to the US unit if the problem units are US, or the SI units if the problems are in Newton and meters. So let's see one example on this. So let's solve this example. So for this example, it says that this man pushes on the 50-kilogram crate with a force of 150 Newton. Determine the power supplied by the man when the time is 4 seconds and the coefficient of kinetic friction. So we know that, so it needs the power B and the coefficient of kinetic friction, which is it's given. The coefficient of the kinetic friction between the floor and the crate is mu k is equal to 0.2. The crate starts from rest, and make sure that the force direction, you know the force direction very well. So here is given 150 Newton, but it is not horizontal. It has an angle, and it gives you the opposite and the 3, 4, 5 triangle, so you can get the components of the force. So first of all, to get the power, we need to know the forces acting on the problem. And actually, if you analyze this force, so let's analyze this force, and I would recommend that you draw a free body diagram. So let's draw a free body diagram. Here's the crate, here's our box, and here is the force provided by the man, F, and it's given that it's not a smooth friction, so it should be there's a friction, but we will write it in a few seconds. And we know that there is a weight. Let's do it in another color. There is a weight go down, and there is normal force perpendicular to the surface in this direction. And let's draw the kinetic. So this is the free body diagram, and this is the kinetic diagram. And this is X, and this is Y, and let's assume that the crate actually should be moving this way. So this is the MA X, and there is no MA and Y because this is the direction of the motion. It never happens that this crate will move up there with this set of forces. So with the motion assumed in this direction, we can know that the friction will be in this direction. So here is the F friction. So to determine the power, we need to know, like here from this equation, the power is the force multiplied by velocity. We need to know the velocity of this box. So let's get the velocity of this box. And to do this, we need to know the acceleration first. So let's start this. And to know the acceleration, you will have to start with Newtonian kinetics. So let's put here, Newtonian kinetics. So if you want to know how to start this problem, the required in this problem is the power, and we know that the power is the F multiplied by V. We know the F because it's given here, the F, but this is not the total F that causes power, because there's some of this force, the force is going like this, and this is the only component that can provide energy to this, and this one is wasted. So here's like Fx and Fy. So we almost like tentatively know what is the F, just like we will get the components of this. But what we don't know is the velocity of this box at t equal 4 seconds. That's what we need to know. And to know this, we will have to use the set of forces to get the acceleration, and use the acceleration with our kinematics background to get the velocity. So let's use Newtonian kinetics, and let's start by the sum of forces in the y direction. So summation Fy is equal to MAY, and we know from here that there is not any acceleration in the y direction, so this will be 0. So let's see what forces we have in y direction. We have N in the positive direction of y, so it will be N, and we have the weight minus W, so it's given 50 kilogram. And we have F, it's going also down there, but it is one component of F. So we know this triangle is, here is 4, and here is 3, and this will be 5. So the component in this direction will be the opposite to 3. So this will be F multiplied by 3 over 5. And this will be F multiplied by 4 over 5, or you can get the theta, and after you get the theta, you know that tan theta will be equal to 3 over 4, and then you get the F cosine and F sine, and it will be these values. And this will be like the y direction component is F, which is, let's put it in simples, multiplied by 3 over 5, and all of these will be equal to 0. So we will have N minus 50 multiplied by 9.81, because the mass is 50 kilograms, and minus 150 multiplied by 3 over 5, and this, all of this will be equal to 0. So now you can get N, and N will be equal to 580.5 Newton. With this, you will be able to get the friction force, because you know that the friction force is always equal to mu k multiplied by the normal force. And we have mu k is equal to 0.2 given in this problem, and the normal force is a 580.5, and this should give us the F friction. Actually, I don't have a calculator, but you will get this, and then you will get the sum of Fx direction, and this will be equal to MAX. So we first applied this in y direction, and second we will do the x direction. And in x direction we have only the friction and one component of the force, and the friction is in the negative x direction, and the component of the force in the positive direction. So let's put the positive first, so it will be F multiplied by 4 over 5 minus the F friction, which is 0.2 multiplied by 580.5, and all of these is not equal to 0. It will be equal to the mass 50 multiplied to AX. So we know everything in this equation here is F is 150. Then we will be able to get the AX. So this is just a simple Newtonian 2D kinetics to get the AX in this problem, and this will give that AX equal to 0.078 meter per second square. As the force on this problem is constant and the friction is constant and none of them is changing over the time, so I can make this acceleration is constant over the time, is not changing because the force is not changing, the friction is not changing, it's mu, and the weight, the normal, all the things in the settings in this problems are constant, so the acceleration will be constant as soon as the force here is not changing over the time. So with this, we will be able to use the kinematic equation that says that V equal V naught plus A multiplied by T. And this came from A equal dV dt. So if you integrate this equation, A dt equal dV, it will give you that A multiplied T minus T naught will be equal to V minus V naught. And this will finally give you this equation. So V naught, it starts from rest, like this crate starts from rest, so V naught will be equal to 0, and what is required here is at time t equal 4 seconds. So, and actually, this is t minus t naught, and it starts from rest, so the t naught is equal to 0, and you will end up with a multiplied by t, and this will be equal 0.078 multiplied by 4 seconds, and this will give you a velocity of 0.312 meter per second here. So this is the velocity. Then finally, we'll be able to get the power. The power will be equal to the F vector multiplied by the V vector. And we know that the V is in this way, the velocity. And as soon as the velocity is in this way, so the only force that can cause power is the force in this way. So this force will not exert any power, just this force. So, or you can actually say it will be F multiplied by V multiplied by cosine theta. And it should give you the same thing. So the total F is 150, and the cosine theta in this equation will be 4/5 multiplied by V, which is 0.312. So this is the horizontal component here. So this will be F cosine theta. So either is fine. If you were able to get the component in the V direction, which will be F multiplied 4/5 multiplied by V to get the power, so that's okay. If you want to use the total amount of force and do the dot product, the magnitude of the first multiplied by the magnitude of the second multiplied by cosine theta, that's fine. It will give you the same thing because cosine theta will give you the component of the force in the V direction. So both should give you the same answer. So this will finally end up with the power will be equal to 37.4, and this is Newton meter over second, or you can put just Watt, W. So this is the unit of the power. So this is how to solve the power equation. You just have to find the velocity of the body so you can get the power. Or sometimes it's messing like the force, or sometimes you are given the power and you will have to find the velocity, or you are given the power and the velocity and you will have to find the force. So some of them should be messing like here's the main equation. So sometimes you will be given the power and you will be given the velocity and you will be asked to get the force, and sometimes you will be given the power and the force and you will have to get the velocity, or any of them, like one of them should be mapping. So let's see this second problem that we have here. So it's also still a power problem, but before we start this, actually let's make it after this problem. Okay, so let's example. So in this example, it says that this winch pulls a 800-pound log up on a slope of a 30-degree at a constant velocity. Just be careful here. The velocity is given, so this is moving with constant velocity, so the acceleration is 0, using 6 horsepower output. So we have here, this winch has an output power of 6 horsepower. So what is required in this problem? What is the coefficient of kinetic friction of the surface? And if the power delivered to this winch, I mean like there is an electrical power delivered to this winch is equal to 3740 feet-pound per second to this winch to get you the mechanical power to lift this log. So what is the efficiency? And we will talk about the efficiency after we are done with the first requirement in this problem. So let's start first. Let's draw our free body diagram. So here is our surface. It has an angle 30-degree. And here is our log or our body. And let's also draw the okay. So here is, let's assume this is the x direction and this is the y direction. And actually here, it doesn't matter because it says that this velocity is constant. So we know that the acceleration max in this direction is equal to 0. But anyway, the body is moving this way. And let's put the forces on this body. So this body has a weight, W, and there is a normal force, and it's moving this way. So the coefficient of kinetic friction, sorry, the friction force will be this way. So, and is there any force missing in this problem? Did I miss any force? Like
The pulling force from the winch?
exactly, yeah. So here we have a wire or a cable that pulling up, let's make it T, or you can call it F, whatever you want, because usually this is a wire and it has tension. So the force here will be equal to the tension in this wire that being pulled by the winch. So let's first use Newtonian kinetics to get the missing forces, because here it's given the horsepower of the winch, but it doesn't give the force T. If we want, we can get it right now. So we can start with this, or we can start with the Newtonian kinetics, whatever works for you. So here you can use this piece of information first, or you can solve this forces first, whatever works for you. So let's start with the power. 1 power. So power will be equal to the force vector multiplied by the velocity vector. And here we know that the velocity in this way and the force in this way. So if we put FV cosine theta, theta will be equal to 0 because the angle between here is the force and here is the velocity. So the angle between them is 0. So cosine theta will be 0. So it will be 1. So this will be 1. So it will be F multiplied by V. So we know that the power is 6 horsepower, so it will be 6. And don't forget to transform the horsepower into our units. So here, the 1 horsepower is equal to 550 pound-feet per second. 550. And this will be equal the force that we don't know. We mean that the force in this cable multiply the velocity of our body, which is a constant 4 feet per second. So now we can get the force, and when you get it, it will be equal to 825 pounds. So we got the force first. So second, let's apply Newtonian kinetics so we can get the F of friction. And after we get the F of friction, we will be able to get the mu k, which is the first requirement in this problem. So let's start with the equation in the y direction. So sum of Fy will be equal to MAY, and we know that there is not any acceleration in the y direction. So let's see what forces we have in y direction, and make sure here we have the y is going this way, and we have the normal force, so we don't have the xy axes like this. So it's better to rotate the axes with the direction of motion, so we can have only one direction that has, like, if we, for example, if we don't know that max is equal to 0, so we only have ma in the x direction and the other direction is 0. But if you make your axes vertical and horizontal like this, and you know that the acceleration is in this way, you will end up with, you will have max and may. So if we rotate this axis like this, and we have the x and y like this, so we made all the acceleration in the x-axis, and we made the acceleration in the y-axis equal to 0. So this will make the problem more easier. So here we have it right, x and y in this direction. So let's see what forces that we have in y direction. So we have n, and it's in the positive, so it will be n positive. And this angle is 30 degrees, because this angle is 30 degrees, so this will be 60, and this will be 30 because it's a 90 degree. So, and w is going down and y is going up, so this will be negative w cosine 30, and we don't have any other forces in the y direction, and all of these will be equal to 0. So n will be equal w cosine 30, and we know that w is 800 pounds. So the normal force will be 692.82 pound. So this is n, 692.82 pound. And let's get to the sum of fx. And we know that the velocity is constant, Vx equal constant. So that means that Ax equal to 0. So let's see what forces that we have in x direction. So we have the force in the cable in the positive x, F, and we have F of friction in the negative x. And we have the component of the weight, negative W sine theta, and all of these will be equal to 0. We calculated F here. So this will be 825 minus F of friction, which is mu k, multiplied by n, and we got n here, 692.82, minus w, 800 sine 30, and all of these will be equal to 0. So here, we only have one unknown, which is mu k. So you can get mu k, which will be equal to 0.61. So right now, it's given in this problem, the power and the velocity. So that's what we did. Get the power and you have the velocity. So we got the force in the cable, and we use this force in Newtonian. So we got F, and use this F in Newtonian kinetics to get the normal force, and then apply it in x direction to get the mu k, which is the kinetic friction coefficient for the surface. So let's move to the second requirement in this problem, which is the power, the efficiency of the motor of the winch. So the efficiency, as you all know, we call it EM, the efficiency of a motor. The efficiency is the ratio of the power done by a machine to the power done on the machine. Like if you have a motor like this, and this motor takes electrical power and the unit will be watt, and deliver mechanical power, and the unit is watt as well. So usually there's losses in the system. Sometimes like it never like, sometimes it could be 100% if the system is fully pure, but it never will be more than 100%, I mean the efficiency. So the efficiency, EM, is equal to the power out of the motor over the power in the motor. So if we know the in and we know the out, so we divide the out over the in to get the efficiency of this motor. So in this problem, it's given the power delivered to the motor means like the electrical power is a 3,740 feet-pound per second. So what is the efficiency of the motor? And here it's given the mechanical power that this motor will able to do to lift this body. So it's very easy now to get the EM. It will be the B out, which is given 3740 over the 6 horsepower multiplied the 550 as a transformation. And this should give us, oh, sorry. Did I switch it? Yeah. So this is the power delivered to the motor. So here, this is the electrical power delivered to the motor. So this should be down. And this is the mechanical power. So 40. Oh, sorry. Again. And we know that the out power, the mechanical power, is 6 horsepower multiplied by 550. And this should give you 0.882. So if I did the other thing and I went in the, like, this is the right, and let's do the wrong. EM will be equal to over 6 multiplied by 550. This will give you a number more than one, so you know that you have something wrong in your problem, and you should check your problem. So because the efficiency of the motor or the efficiency of the system will never reach more than 100%. So you will like reverse, like put this up there and put this down there, because this is the input power, this is the output power, and this is the input power. So you will get a number that less than 1, less than or equal if the system is fully efficient. So does anybody have any question on the power and efficiency? Or also, yeah, power and efficiency, yeah, or any question on these problems? Okay. So with this, let's move to another topic, which is similar to the work. Chapter 14.5, conservative forces and potential energy. Okay, so based on the last couple lectures, we identified the work from point 1 to point 2 is equal to S1, the integration from S1 to S2, F cosine theta multiplied by ds. And from here, we will able to get the work done by gravitational force, which is W delta y, the work done by a weight, and the work done by a spring. And we said that the work done by a spring is always negative, K S2 square minus S1 square, and the work done by a constant force, which will be equal to F constant cosine theta S2 minus S1. And this is how we conceptualize the work done by the different types of forces. So let's think about this work with different mentality. So let's define first the kinetic energy and the potential energy. So the kinetic energy is the measure of the particle capacity to do work, which is associated with the motion. So let's have something like this. Here's our particle, and our particle will move from here to here. So if we give this particle a certain type of forces to move from here to here and change the velocity from like v1 equal to 0 to v2 equal to 4 meters per second. So the energy given to change the velocity of the particle is called kinetic energy. So we give some energy to the particle to change its velocity from rest to be 4 meters per second. That's why we call the kinetic energy T1 is equal to half mv1 square, and T2 is equal to half mv2 square. And this is the change in the kinetic energy. From T1 to T2, the velocity changed from V1 to V2. So the kinetic energy is the amount of work exerted on the body to change the velocity of the particle from V1 to V2. So how about the potential energy? Potential energy is a little bit different from the kinetic energy because it's not related to the velocity, not related to changing the velocity of the particle. It's about it changing the position of the particle. So here, let's assume that we have the ground. Here's the ground. And let's assume this is our datum. And you stand here and you have a soccer ball and you throw the soccer ball up there. And this is your data. Once the ball is here, the soccer ball get an energy is called potential energy because it has some energy that will let this ball come down. So, and this is called W Y. Depends on the how high the ball reach. So once the ball get here, it has a potential energy to go down. But once the ball rests on the ground, it doesn't have any potential energy. It's a zero because it can't go down, cannot get down. But if the ball is down here and you want to bring it back to the ground, so it has a negative kinetic energy, and you will have to exert some effort on this ball to move it from here to here. It cannot get by itself. So the ball cannot get from here to this position by itself. So this, if we have this is negative y, because this is our datum. So the potential energy of this ball here is equal to W multiplied by negative y. And here, the kinetic energy will be W multiplied by 0 because it's neutral. It will not go up or not go down. So this is how is the definition of, we defined this in terms of work before, but right now let's define it in terms of energy, like how much energy that the body has to come back to its original position. So if you throw the ball up there, it has some energy to come back by itself. So it's a positive energy, positive potential energy. And if it's down there and wants to go up, it cannot go up by itself. So you will have to give it some, do some work or give it some energy to bring it back. So it has negative energy and needs a positive energy to come back to its neutral axis. And that's what we call, so kinetic energy, we called it before, it's T. The potential energy is called V. And if we are talking about gravitational potential energy, is called Vg, and it's always equal to W multiplied by Y, and Y could be positive or could be negative, depends on the elevation of the body from a certain datum. So you will have to define where is your datum, and then you can measure if it's above or below the datum. If it's above the datum, it will be positive. If it's below the datum, it will be negative. So this is the potential energy, and we call this, it's a conservative energy. So what do we mean by conservative? So conservative mean that the work exerted or the energy exerted is independent on the past. Like if you have your soccer ball, like you are standing here, and you throw the ball, it doesn't matter if the ball goes like this or goes like this or goes like this. It doesn't depend on the path. It depends on the elevation. But the like here, it goes here up to here. So whatever the path is, it only depends on the elevation of the body. What is the height? What is the elevation from the datum? So this is called a conservative energy. This is completely different from the friction. Like let's assume that we have a surface like this, and you have your body here is moving on this surface. So the surface is always depends on the path. So the longer the path, the more friction that will be exerted on the body. So the friction force is not a conservative, non-conservative force. And also if you have a force that acts on the body like this, so the force here, it's changing, it's like, let's assume that it's something like this. So the theta between the force and the surface is keep changing as you have the body here. Sometimes like the force will be something like this. So the theta keep changing. So it depends on uh, the path of the motion. So it's a still non-conservative force. So the first conservative force that we have, number one, is the potential energy from the weight, and number two is the spring force. So let's assume that we have a spring like this. And if you have your spring at this location and you stretch it, the spring to this location. So this is the new position. So you put some forces and the spring will have force here. And the potential energy of the spring, so whenever you pull this, the spring will have a potential energy to come back on its own. It doesn't need you to come back. Once you release this force, it will have an energy that enables the particle to move from here to here. So the potential energy of the spring, VE, is always positive because it always has an energy to move back to its original position, even if you compress this spring. Like if the spring come here and you put it here and you put some compression, so the spring, once you release this, the force here, the spring will come back to its original position. So whatever it's in compression or in tension, the spring itself has a potential energy to come back to its original position. And this energy is always positive, and it equals to half oh, half K S squared. This is in terms of the energy, and this is the only two energies that called potential energy. The one derived by the gravitational potential energy, this one, and it's the W multiplied by the Y of your body. And the second one is the elastic potential energy done by a spring, and this is how we got them. So let's put the equation here. The total potential energy is equal to Vg plus Ve. So this is the total potential energy. If you have, like, for example, you have a spring and there's a mass, and you compress this spring up there, and if this is your datum and your mass is here and the spring is compressed, so you can get the potential energy from WH, and you can also get the potential energy from the spring, which is half Ks square, which is the compression in the spring. So this is if we want to get the total potential energy stored in the system. And it should be positive because this body, once it's released, it will have energy on its own to come back to its original position here. And if we want to write our general equation for the conservative and non-conservative energies along with the work, we know from the last time that the work from 1 to 2 is equal to T2 minus T1. And we included everything here. We included the work done by a force, and we included the work done by spring, and we included the work done by the weight. We included everything here, but we can write this equation in a new form. So let's see how can we write it. It's the same thing. You can either use this equation and deal with the problem as a work and kinetic energy, or divide the equation into conservative forces and non-conservative forces. So here's the new equation. Like if we put this equation, if we put T1 in the other direction, so it will be T1 plus U from 1 to 2 will be equal to T2. So here's the new rule. It says that T1 plus V1 plus U from 1 to 2 equal to T2 plus V2. This is a new mentality for this equation. So let's see what's different. So what different is that we excluded the spring work from U1 to U2, and we included the weight work, and we put them in V1 as a potential energy. Does anybody
I have
have
a
any
quick
question?
question on the notation.
Yeah.
So the V that you're using in that final location, in that final equation, that's going to be the kinetic energy, right?
No, the kinetic energy is T,
Okay.
T1 and T2. V1 is the potential energy done by a spring or a weight.
Okay. Thank you.
Yeah. So here's, I have them. Here's the kinetic energy is T, and the potential energies are V, G, and V, E.
Okay. I missed yesterday's lecture, so I wasn't completely sure on the notation of that. But thank you for the clarification.
It's time to introduce V today. So the last couple lecture you only saw T's. T is the So this equation from the last time, it will be half mv1 squared, because this is how T1 looks like. And the work from 1 to 2 will be equal to half mv2 squared. But U1 to U2 should include the work done by all the forces. The work done by the force, the non-conservative forces, and also the work done by the weight. and the spring. So this equation is just a new mentality to solve the problems. Just exclude the weight and the spring and put them in V1 and V2. And I will prove in a few minutes that both will give you the same answer. Okay, so let's continue with this one. So T1 will be, we know that T1, let's put the equation, this equation here. T1 will be equal half mv1 square. And V1 is the potential energy done by the weight and done by the elastic spring. And this will be equal to W, which is mg, because we know that Vg is equal to W delta y. And W is equal to mg, and it will be delta y. So we can put mg h1. So let's call the, not delta y, sorry, it's y. Because we don't have delta here. So it's just y, and here's y. And y is the height from the datum. And right now, let's assume that it has y is equal h1, the height from the datum is equal to h1, and the spring is v e is equal to half k s square, and this will be half k s1 square, because this is v1, plus the work done by the non-conservative forces. And let's put non-conservative forces, and this includes the friction and force on the bath. And this should be equal to half mv2 square, which is T2, and V2 is the Vg plus Ve, which will be plus mgh2 plus half k s2 square. So this is the full equation of the conservative forces. So let's see that this equation, let's see how this equation is the same as the equation that we learned from the last lecture. T1 plus U12 equal to T2. This is the equation from the last lecture, and U1 should have the force, weight, and spring. Okay, if you, for example, got the MH2 and put it in the other side, and got the half k s2 square and put it in the other side, so this will give you half mv1 square plus mg h1 minus h2 plus half k s1 square minus s2 square plus u12 will be equal to half mv2 square. As you remember from the last time, that this is equivalent to negative half k s2 square minus s1 square. Just get the negative outside and swap s2 with s1. And this is the mg is the w, and h1 minus h2 is the delta y. And if we put this 2 in u1, u2, because we calculate them as a work, this will give you half mv1 square plus u1 2 half mv2 square, which is t1 plus u12 equal to T2. So the concept is the same, but we divided it into components and deal with its components as energy. And actually, you are free to use in your problems to use this concept or use the work concept that we learned it from before. Like assume that the weight exert work and the spring exert work and include all of them here, or you use this equation as an energy and see what is the kinetic energy and what is the potential energy at the position 1 and what is the kinetic and potential energy at position 2, and get only the work from the non-conservative forces and solve your problem. Like, for example, here you have your body, and let's assume, like, for example, I think we had a spring problem last time, and this is the initial location, and this is our spring, and the body came here. So you can deal with this problem. You can get the spring half ks1 square and half ks2 square and put them in this equation, and also get the, like, assume that this is the datum and calculate h1 and calculate h2 and put it in this equation, and only get the force due to friction if there's a friction, and the weight and all the other forces, and put them in U1, 2. It should give you the same answer. So just like it's a new mentality to solve the problem by getting the potential energy V and the kinetic energy T at position 1, and also get the potential energy V2 and the kinetic energy T2 at position 2, and solve this equation. So it's the same thing. Like if you want to use this or use that, and actually next time I will start our lecture by solving a problem using this concept and actually using our old concept, and I will prove that both will give you the same answer. So do you have any other questions? Anyone on the meeting?
No, that's good for me. Thank you.
All right, that sounds good. So that's all for now. And guys, keep attention to the announcement, because I announced the midterm exam date. It will be on Monday. I think Monday, July 12th. Yeah, Monday, July 12th, in the regular time of the lecture, and it will cover chapter 12, 13, 14, and 15. So just be prepared, and we have a quiz next Friday at 10:15, just after the first 30 minutes of the lecture, and it will cover the chapter 12.10, the relative motion, and also chapter 13, which is the force and acceleration. So just like to know what you will be examined in. And see you tomorrow, David.
Thank you, Professor. Have a good one.
Thank you.